Wow, it's so hot today.
It doesn't feel any cooler in here.
Darn, my thermostat must be broken. If I knew how my thermostat worked, I think I would be able to fix it.
I found a YouTube video. Some professors are calling it a PID controller.
Welcome back to Cone Academy. Before we begin, don't forget to like, subscribe, and share this video. Today, we are talking about PID controllers. PID stands for Proportional Integral Derivative. Simply put, PIDs are controller methods that try to regulate some form of measurement. PIDs exist in almost everyone's daily life. They can be in form of thermostats, baking ovens, and even cruise control in a car. PIDs have three important parts: the sensor, the output, and the brain. For example, in a thermostat, the sensor measures the current temperature, the output heats up or cools off the room, while the brain tells how much the output should heat up or cool down the room, depending on what it receives from the sensor. Let's start off with the proportional part of a PID. As we all know, any equation following y equals n times x is considered proportional. From this, we get an equation y is equal to kp times e. Continuing the example of a thermostat, y is the power that the output to heat up or cool down the room, kp is a proportional constant, and E is the air, which is the difference in current temperature and target temperature. Using just this equation, we can get a temperature that will change over time.
That makes sense, but wouldn't it result in a constant offset if there was an issue with the sensor?
I guess so. That means if the sensor temperature was off by 1 degree Fahrenheit, then the target temperature would be off by 1 degree.
To fix the offset from only proportional control, we can constantly sum the error to determine if the value is getting closer to the set point. The sensors and thermostats check the temperature at discrete time intervals, so we must use a Riemann sum to approximate the error from the set point.
So we use the trapezoidal sum to approximate the output. Using the equation, we sum the proportional, the integral terms, which is ki times the integral of the error, and the derivative term. At time equals 2, the length of the interval is 1, and the two heights are 20 and 14.9, which yields an I value of 2.6. Adding the p and t terms, we get 5.89, which subtracted from the last value is close to the computer output. This process is repeated for each point.
By summing the error, the PI controller is able to respond to an offset or abnormality, even if the error is equal to 0, and it allows for present stability. The integral is the most important of the three controls, and many industries just use the PI controller because of the efficiency and accuracy it provides. As you can see in the diagram, the integral term has a huge effect on the method for reaching the set point. Although this control is immensely useful, it does add complexity. There are a large amount of variables, and calculating them at every iteration can slow down the machine. Also, if the error becomes way too large, the process can't be controlled until the error is sufficiently small.
While using just the proportional and integral equations will suffice in most situations, using a derivative will make it even better. As seen when using an integral, our temperature will often oscillate. This is because as the temperature approaches the target temperature, the output is still on a high power, overshooting the target temperature. To counter this, the derivative, or the change in error over time, is used. For example, when the change in error is high, the derivative will try to limit the change as to decrease the overshoot and decrease the oscillation in temperature. You could see the effects of the derivative in a comparison to using the integral without the derivative.
Oh, I get it. So the derivative attempts to make sure that as the temperature reaches the target temperature, the power of the output is decreased, so that the temperature won't have as much of an overshoot.
And that would make the actual temperature closer to target temperature if we only use the integral and derivative.
As you can see, using a PID controller will net you with the final equation seen here. It sums the proportional control, the integral control, and the derivative control. This equation will not be very efficient unless you use good values for Kp, Ki, and Kd. To find those constants, you'll need to do trial and error to find which is best for your situation.
Thanks for watching. If you enjoyed the video, smash the like and subscribe button and comment your favorite use of PIDs. Also, check out my Patreon, linked in the description below.
Wow, we learned so much from that video. Now let's go fix that thermostat.
5 hours later.
I think we fixed it.
It feels much nicer now.
Who knew how useful PIDs could be?
I certainly didn't.